Hello and welcome. If all we want to do is determine if an improper integral converges or diverges, and we don't care about the value that it converges to, then sometimes we can use what's called the comparison test, where we compare the improper integral that we're interested in to another improper integral that we know either converges or diverges. So it says, suppose f and g are continuous on the interval from a to infinity, and 0 is less than or equal to f of x is less than or equal to g of x in that interval from a to infinity. In other words, you have both f of x and g of x are non-negative numbers. They're either positive or 0. I'm going to write both f and g are non-negative. In other words, they're either on or above the x-axis. That way, when we're talking about the areas under these curves, they're really going to all be positive areas, or possibly 0. They won't dip down, the functions won't dip down and become negative, causing negative areas to have to deal with. So we have these two functions, f and g, where g is the bigger function and f is the smaller function. That's the key here. Now it says if the integral from a to infinity of g of x converges, then the integral from a to infinity of f of x also has to converge. In other words, if the values of g are bigger and the integral manages to converge to some finite number, then the integral of a smaller function, one with smaller y values, is going to have to converge as well, because the area under that curve with smaller y values is going to be smaller. Figure 9 shows a picture. Here we have g of x on the top, it's the bigger function. F of x below it, it's the smaller function. And what it's saying is that if from 1 to infinity g of x converges, so in other words it has a finite area under it, then f of x has to converge as well because it's got smaller area under it. And then the reverse, there's like a reverse case as well. So it says if the limit, if the integral as a, thinking limits here, if the integral from a to infinity of f of x diverges, so it blows up to have infinite area, you can think, then the integral from a to infinity of g of x, which is bigger, is also going to have to diverge because it's got more area under its curve. So if already the integral from, say, 1 to infinity of f of x diverges, like the case was for 1 over x, then a bigger function, like let's say 2 over x, is going to have to diverge as well because there's more area that you're adding under g of x, under the bigger function. All right, so let's use this comparison test to help us with example 6. Example 6 says, does the integral from 1 to infinity of sine squared x over x squared dx converge or diverge? Now, off to the right, we have a picture of sine squared x over x squared. And basically, it looks like the 1 over x squared function, but it kind of wiggles up and down. So it touches the 1 over x squared function at its peaks. But then it goes down to 0 whenever sine squared x goes to 0. So it kind of waves up and down as you go to the right. Now, one thing is it's a little hard to find an antiderivative of sine squared x over x squared. But we can still answer the question, does it converge or diverge, without actually finding the antiderivative. What we can do is we can say, we know that the sine squared x function, if we just look at sine squared x, what can we say that sine squared x is between? What are the possible range of outputs of sine squared x? So if you said 0 to 1, then that would be correct. Sine x by itself outputs values from -1 to 1. But sine squared x will take any of those negative outputs and make them positive. So that makes it so that you only get numbers from 0 to 1. It's possible to get an output of 0 if, like, you input an x value of 0, then sine squared 0 will be 0. And it's possible to get an output of 1. You could plug in pi over 2. But those are the only range of possible outputs of sine squared x. So starting from this, what we could do is divide by x squared. We're going to divide all 3 parts by x squared. And the reason we're doing that is because the function that we're interested in is sine squared over x squared. It's sine squared divided by x squared. So if we take 0 divided by x squared, we get 0. Sine squared divided by x squared is our function that we're interested in. And then 1 over x squared is 1 over x squared. So this is great because now we've got this inequality that we need to make comparisons. Now we've got our function, which we're going to call f of x, to match the comparison test explanation that we were just talking about. And then we've got a function that's bigger than it. Notice that both of these functions are non-negative, right? They're greater than or equal to 0. Both of these functions are. And here, this 1 over x squared function is bigger than our sine squared x over x squared function. So what this would be saying is that the way we could use this is we could say if 1 over x squared, if the integral of 1 over x squared from 1 to infinity, if that converges, then this smaller function that we have has to converge as well when we take the integral of it from 1 to infinity. That's what we're going to write over here. We're going to write since the integral from 1 to infinity of 1 over x squared dx converges. Now how can I know that the integral from 1 to infinity of 1 over x squared dx converges? There's something from one of the previous videos that we learned. So if you said we know that because we figured out all of the integrals from 1 to infinity of 1 over x to the p in general, then that would be correct. So we know that 1 over x squared converges because it's like 1 over x to the p, the integral from 1 to infinity of 1 over x to the p, where p is equal to 2. And as long as our p value is greater than 1, we know that 1 over x to the p will converge when we take its integral from 1 to infinity. And I should mention that that works for not just 1 to infinity, but also any number to infinity. Because it doesn't really matter what x value you start your interval in. It just matters what happens as you go to infinity. That's really what's going to determine whether or not the integral converges or diverges. So since the integral from 1 to infinity of 1 over x squared dx converges, because there we have a 1 over x to the p, where p is equal to 2, and that's greater than 1. Again, we're leveraging that work that we did in a previous video. Then we know that the integral from 1 to infinity of a smaller function has to converge by comparison. So the integral from 1 to infinity of sine squared x over x squared dx also converges. And this is by the comparison test. Okay, so example 7, here we have the integral from 1 to infinity of 1 over the square root of x squared minus 0.1 dx. Now we could go and try to find an antiderivative. We could use some kind of trig substitution. But if all we want to know is does it converge or diverge, then we can also try to use a comparison test instead. So here's how we can do it. We can say 1 over the square root of x squared minus 0.1. It's that 0.1 that's really messing things up. So if we get rid of it and we have 1 over the square root of x squared, and we think about what the relationship is between those two numbers, well, here we can think if we add 0.1 inside of the radical, so adding something to the bottom of the fraction, that new fraction will be smaller, right? the bigger the bottom of the fraction is, like the square root of x squared is going to be bigger than the square root of x squared minus 0.1. So the bigger the bottom of the fraction is, the smaller that overall fraction is. So we can write that the original one, 1 over the square root of x squared minus 1, is bigger than the 1 over the square root of x squared. But 1 over the square root of x squared just is the same thing as 1 over x, at least when x is positive like it is here, right? All of the x values from 1 to infinity, those are all positive x values. So we can make that simplification. And we know that all of these are greater than or equal to 0, right? So these are non-negative functions that we're dealing with. So now we can say, since the integral from 1 to infinity of 1 over x dx, what does that do? Does that converge or diverge? So if you said it diverges, that's correct. And that's because either example 1, we showed that it diverged, or you know that this is like 1 over x to the p, where p equals 1, and 1 is less than or equal to 1, which is the case where the integral diverges. We said if p is less than or equal to 1, then your integral, your improper integral, is going to diverge. So since that integral diverges, the bigger integral, so the bigger function, the integral of the bigger function, that is going to have to diverge as well, because it's more area under that curve. So the integral from 1 to infinity of our function, the 1 over x squared minus 0.1 dx, also diverges. This is by the comparison test. Oops. Figure 12 just shows a picture of what 1 over the square root of x squared minus 1 looks like. It looks really similar to 1 over the square root of x squared, which is like 1 over x, but just a little bit above it. It's a little bit of a bigger function. So lastly, just want to mention the note. Sometimes you can't use the comparison test, unfortunately. We had those two cases, but those don't cover everything. And when you don't fall into one of those two cases, where you know that a bigger function converges and therefore a smaller function would have to converge, or if you know that a smaller function diverges and then the bigger function would have to diverge. And when I say that the functions are converging or diverging, really I mean the integral of those functions. I'm just using a shorthand way of saying it. But then there are other cases, like what if you have a small function converging? Does that say that a bigger function has to converge? Well, you don't know. It could be like not that much bigger and still converge, or it could be a lot bigger of a function and it can diverge as an integral again. So it's, in that case, you don't really know. So if you have the inequality direction in the wrong direction, then it may not really work out that you can use the comparison test after all. So the note gives an example. The integral, if we just took the last example, example 7, and switched the sign from a minus 0.1 to a plus 0.1, so we have the integral from 1 to infinity of 1 over x, square root of x squared plus 0.1 dx. Here, you'd want to make the comparison to 1 over the square root of x squared, because that's what you can compare it to, like a 1 over x kind of function. But the problem is the inequality would go in the wrong direction. You would have the inequality direction that we had in example 7 flipped, so you'd have 1 over the square root of x squared plus 0.1 is less than, and you could put or equal to if you wanted to. The equal to is optional. 1 over the square root of x squared, which is 1 over x. But here, again, the inequality is going in the wrong direction. Knowing that the integral from 1 to infinity of 1 over x diverges doesn't say anything about the integral from 1 to infinity of a smaller function. A smaller function could still diverge, because it could possibly be not small enough, or it could converge. It could be small enough to converge. It just doesn't say anything. It's inconclusive. So in that case, you might have to go and try to find an antiderivative or something else. All right, so that's it for this video. Thank you for watching, and see you next time.